Introduction. Prince and his father are standing at the window side and viewing outside. It is a rainy weather. Suddenly, lightning occurs and falls down. Prince observed that the tree on the road catches fire due to lightning. He asked his father that why tree catches fire and the car remains safe on the road. His father replied him that it's due to electrostatic shielding. When lightning falls on the car, then all the charge flows through the other surface of the car and then grounded. But in case of the tree, it does not happen. Students, you must be more curious to know and learn this fact and topics. So let's study more about this in the chapter Electrostatic Potential and Capacitance. Objectives. At the end of this lesson, you'll be able to define electrostatic potential, calculate potential due to a point charge, system of charges, and an electric dipole, define principle of superposition for electric potential, define equipotential surface, define potential energy, calculate potential energy of a system of charges and electrical dipole, know electrostatics of conductors, explain electrostatic shielding. Electrostatic potential. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Electric potential is measured in volt. If 1 joule work is done in moving plus 1 coulomb charge from infinity to a point in an electric field, then the potential at that point is 1 volt. The potential difference between 2 points A and B is given by VAB equals WBA upon Q0. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential point. Potential due to a point charge. A point charge plus Q is situated at a point O in space. This charge creates its own electric field E around itself. We have to calculate the potential of this electric field at point A. We consider two very close points, P and Q, on the line OA. The total work done in moving plus 1 coulomb charge from infinity to point R is given by W is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R. This amount of work is the potential of the electric field created by the point charge plus Q at a distance R from Q. We can show in the graph that, as R increases, the potential falls down hyperbolically. If point A is at higher potential than point B, then the potential difference between the 2 points is given by VAB equals VA minus VB. Put the values of VA and VB, we get VAB is equal to Q by 4 pi epsilon naught multiplied by 1 upon A minus 1 upon B. Principle of superposition for electric potential. Let us consider 2 point charges plus Q1 and plus Q2. Take any 2 points A and B in the combined electrostatic field of 2 charges Q1 and Q2. Choose a curve L between A and B. We know that VB minus VA is equal to minus integration from A to B of E vector dot dl vector. But according to principle of superposition of electric fields, E vector is equal to E1 vector plus E2 vector. Therefore, VB minus VA is equal to minus integration from A to B of E1 vector plus E2 vector dot dl vector. So, electrostatic potential differences are additive. If A is taken to infinity, then V is equal to sum of minus integration from infinity to B of E1 vector dot dl vector and minus integration from infinity to B of E2 vector dot dl vector. So, the electrostatic potential at B is the scalar sum of potential at B due to charge Q1 alone and potential at B due to charge Q2 alone. This result is applicable for any number of charges. Potential due to an electric dipole. We consider a dipole with 2 charges, plus Q and minus q separated by a distance 2L from each other. We calculate the potential of the field due to this dipole at different points. Potential at an end-on point. Consider an axial point P at a distance r from center O of dipole on the side of plus q. The potential at P due to plus q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by q upon r minus 1. The potential at P due to minus q is given by V negative is equal to 1 upon 4 pi epsilon naught multiplied by minus q upon r plus 1. The total potential at P is obtained by having direct addition of the two and is given by VE is equal to 1 upon 4 pi epsilon naught multiplied by P upon r square. This shows that the potential along the axis of dipole falls inversely with the square of distance. Potential at broadside point due to an electric dipole. Consider a point P on the equatorial line at a distance r from the center of dipole. The potential at P due to plus q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by q upon under root r square plus L square. The potential at P due to minus q is given by V negative equals 1 upon 4 pi epsilon naught multiplied by minus q upon under root r square plus L square. The total potential at P is obtained by having direct addition of the two and is given by VB equals 0. This shows that the potential at any broadside on point is 0. Potential in plane of an electric dipole. Consider a point P on the plane of dipole at a distance r from center O of dipole, and PO makes an angle theta with the axis of dipole AB. The distances of P from A and B are R1 and R2 respectively. The total potential at P is given by V equals Q upon 4 pi epsilon naught multiplied by R1 minus R2 upon R1 R2, which is equal to 1 upon 4 pi epsilon naught multiplied by P cos theta upon R square. This is a generalized expression for representing the potential of a field of short dipole at any point on the plane of the dipole. Potential due to a system of charges. Consider the point charges Q1, Q2, Q3 and so on till Qn at distances R1, R2, R3 and so on till Rn respectively from a point of observation P. The resultant potential at P due to all the charges is the algebraic sum of the potentials at P due to individual charges. This is because electric potential is a scalar quantity. The resultant potential at P is given by V as V1 plus V2 plus V3 and so on till Vn. Equipotential surfaces. An equipotential surface is the locus of points at which the potential due to a charge distribution is same. No work is done in moving a charge from one point to another along an equipotential surface. In a point charge for a given radius, electric potential is same, and the equipotential surfaces are spherical surfaces centered on the charge. Electric field lines created by any system of charges are always perpendicular to the associated equipotentials. Example on equipotential surfaces. Let's take an example on equipotential surfaces. An infinite thin plane sheet of charge density 10 raised to the power minus 8 coulomb per meter square is held in air. How far apart are two equipotential surfaces whose potentials differ by 5 volt. Let's see the solution. We know that electric field intensity E is equal to sigma upon 2 epsilon naught. Since E does not depend upon the distance from the plane sheet, therefore E is constant for the given problem. If delta x meter is the separation between two equipotential surfaces which differ in potential by delta V, then E is equal to delta V upon delta x. We evaluate the value of delta x as 2 epsilon naught delta V divided by sigma. By putting the values in the equation and evaluating, we get the value of delta x is equal to 8.85 millimeter. Potential energy. The potential energy of a charge Q present at a point in an electric field is equal to Q times the potential of the field at that point. U is equal to QV. The unit of potential energy is joule. Bringing of any charge Q from infinity to a point A in an electric field E will require a work WA to be done on the charge, which is stored in the charge Q as its potential energy. UA is equal to QVA. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. Potential energy of a system of charges. The potential energy of a system of point charges is the work required to assemble this system of charges by bringing them in from an infinite distance. Potential energy of the system of two-point charges. The electrostatic potential energy of the system of two-point charges is given by U as 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12, where Q1 and Q2 are the electric charges of the 2 points. R12 is their separation distance. Potential energy belongs to the system as a whole and not to any individual charges. Note that the electric potential energy is the product of charge and electric potential. Potential energy of the system of 3-point charges. The potential energy of the system of 3-point charges is the energy required to assemble the system of 3-point charges from an initial situation in which 3 charges are infinitely far apart. The procedure for calculating this electric potential energy is to calculate the potential energy for every pair of charges separately and to add the results algebraically. The electrostatic potential energy of the system of 3-point charges is given by U is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12 plus Q2 Q3 upon R23 plus Q1 Q3 upon R13, where Q1 Q2 and Q3 are the electric charges of the 3 points, and R12, R13 and R23 are their separation distances. Potential energy of an electric dipole in an external field. Consider an electric dipole of dipole moment P is placed in a uniform electric field E. The dipole experiences 2 equal and opposite forces plus QE and minus QE at its ends forming a couple. Magnitude of the torque on the dipole is equal to magnitude of the force into arm of the couple. Tau is equal to QE into 2L sin theta, which is equal to PE sin theta. Work done in rotating the dipole through a small angle d theta is equal to tau d theta, which is equal to Pe sin theta d theta. Total work done in rotating the dipole from an initial orientation theta naught to the final orientation theta is W equals to minus Pe cos theta minus cos theta naught. If the initial orientation theta naught is equal to 90 degrees, then W is equal to minus Pe cos theta. This work is stored as potential energy. Thus, potential energy of the dipole is U as minus Pe cos theta, which can be written as minus P dot E. Electrostatics of conductors. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The electric field is zero at all points in a conductor. The electric field just outside the surface of a charged conductor is perpendicular to the surface. Excess charges on an isolated conductor in an electrostatic condition reside entirely on its surface. Excess charges on an irregularly shaped conductor tend to accumulate at locations where the curvature of the surface is greatest. The electric potential is constant everywhere inside a conductor and equal to its value at the surface. Electrostatic shielding. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding. It is the best way to protect some area in vacuum from the influence of external electric field. Electric field is zero inside a conductor of any shape in electrostatic shielding. If a conductor A kept at zero potential surrounds conductor B, then B is said to be electrically shielded by A from other electric systems. For example, in a thunderstorm accompanied by lightning, it is safer to be inside a bus or car rather than near a tree or open ground. Did you know? Volta had already created the electrophorus to create static electric charges and discovered methane. The volt was officially established in 1881 as an electrical potential of 1 joule per coulomb of charge. It is used around the world. The electric potential decreases in the direction of field and increases against the direction of electric field. Equipotential surfaces and electric lines of force constitute a mutually perpendicular network. Summary. Let us summarize what we have learned. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential points. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Potential along the axis of dipole falls inversely with the square of distance. An equipotential surface is the locus of points at which the potential due to a charge distribution is the same. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding.